Hi, welcome to the Piezo-Metrics channel. I'm Frank, and I'm here to talk about temperature compensating a Wheatstone bridge that uses semiconductor strain gauges. Semiconductor strain gauges are great to use. They're small and they have a large gauge factor. When fabricated using Piezo-Metrics' patented process, creating match sets of 2, 4, and 8 gauges with resistance variabilities below 0.5 to 2% is easily achievable. It's well known that semiconductor strain gauges have a large temperature coefficient of resistance, or TCR, compared to metal foil gauges. For example, a semiconductor strain gauge can have an apparent thermal strain of 975 microstrain for a 1 degree Celsius change compared to a 100 microstrain change for a metal foil gauge. Clearly, it's important to deal with this temperature sensitivity. There's also the fact that for P-doped strain gauges, which are the type of gauge that Piezo-Metrics makes, their resistances will increase with an increase in temperature, and their gauge factors will decrease with an increase in temperature. If nothing is done to counter these behaviors, it's nearly impossible to get a thermally drift-free linear response from a Wheatstone bridge that uses semiconductor strain gauges. In this video, I'll go over the theory of temperature compensation of semiconductor strain gauge Wheatstone bridges. The theory I'm presenting is based on a paper published in the Census Journal in 2016. A reference to this paper is given in the description below. Here's a schematic of an open Wheatstone bridge comprised of strain gauges G1, G2, G3, and G4. The red and black lines are connected to the excitation voltage, and the green and white lines are for the bridge output. The bridge is said to be open because the yellow and black wires at the bottom of the bridge are not connected yet. The bridge is said to be closed when the yellow and black wires are connected together. The open topology allows the strain gauge resistances to be measured individually. This is important as part of the temperature compensation procedure. The temperature compensation resistors are made up of the bridge resistor Rs and some combination of the shunt resistors Rz1 or Rz4 and the series resistors Rb2 or Rb3. The aim of the resistances Rz1, Rz4, Rb2, and Rb3 is to tune the bonded TCR of each arm to be the same. Note that the bonded TCR is different than the TCR of the unbonded gauges. The unbonded TCRs are very closely matched when Piezo-Metrics produces its sets of matched gauges. When the gauges are bonded to a sensing element, small variabilities in the structure, adhesive bond line, and heat transfer response alter very slightly the TCR of each bonded gauge. That's why tuning is necessary. Let's look at how a series resistor like Rb2 can tune the TCR response of gauge G2. Here I use the generic labels R and G. As you can see, they are connected in series. The first equation shows the resistance of the gauge as a function of temperature. G0 is the gauge resistance at reference temperature T0. Alpha is the TCR of the unbonded gauge. For Piezo-Metrics gauges, alpha is positive. We can see that if the temperature goes up, the gauge resistance goes up. When we rearrange the equation to solve for alpha, we get the second equation. Now if we add the resistor R, our equation becomes alpha sub G plus R, which we will call the effective series TCR. The effective series TCR is defined by G sub T, which is a function of temperature, plus the resistance R, which for all practical purposes is pretty much temperature independent. We can see that the R's in the numerator cancel out and we're left with the second equation. Looking more closely at the second equation, we can see what R does to the effective TCR for gauge G. As the resistance of R increases, the effective series TCR will decrease. So we can use R to tune the TCR of the gauge to what we need for bridge temperature compensation. We can go through the same analysis for a gauge with a shunt resistor R. Here is the equation for the effective shunt TCR. The effective shunt TCR is defined by G sub T, which is a function of temperature, in parallel with resistance R. When we rearrange the first equation, we end up with the second equation. Looking at the equation, we see that R appears in the denominator like the effective series TCR. So, if we increase R, we can get the effective shunt TCR to decrease. Turning our attention now to the effect that RS has on bridge output, we can see that RS is in series with the equivalent bridge resistance, R sub B. Remember that R sub B will be a function of temperature because gauges G1 to G4 are a function of temperature. When we write the equation describing the output of the circuit, we have essentially a voltage divider multiplied by the gauge factor, which is a function of temperature, and the load, which we will call P. Note the resistance RS is found, like the series and shunt TCRs, in the denominator of the equation. The temperature sensitivity of the gauge factor is quantified by a value known as the temperature coefficient of gauge factor, or TCGF. For Piezo-Metrics strain gauges, their TCGFs are a negative value. We see that if we do not add a series resistor to the circuit, that is when RS is 0, when temperature increases, the gauge factor will decrease because we have a gauge that has a negative TCGF. The result is that the normalized bridge output defined by Vout divided by the excitation voltage and load will also decrease. To counter the negative TCGF, we can add the series resistor RS to the circuit. If we choose RS appropriately, we can use the increase in bridge resistance to balance the decrease in gauge factor so that the normalized bridge output is constant with temperature. Note that this type of temperature compensation only works if the gauge's TCR is greater than its TCGF, since RS acts to reduce the TCR relative to the TCGF. This is the case for Piezo-Metrics gauges. At Piezo-Metrics, we choose to use this topology for our Wheatstone bridges. Other temperature compensation topologies can also be used. So, why did we choose this particular topology? As we saw in the previous slides, we can add resistors onto G1 to G4 as needed to tune their effective TCRs. With this topology, a series resistor on either G2 or G3 allows us to adjust the zero balance output of the bridge in addition to tuning the gauge's effective TCRs. So, Piezo-Metrics chose this topology because it works for us. Now that we understand what temperature compensation resistors do, we come to the question of how do we calculate their values? Here I show the problem in terms of what is known, what is unknown, and how the unknowns can be calculated. The knowns are the gauge resistances at the zero and full scale loads at the lowest and highest expected temperatures. They are experimentally measured values. We can see now why we need to start off with an open bridge topology. It's the only way we can measure the gauge resistances under the experimental conditions. For temperature compensation of a full bridge, it will take a minimum of 16 measurements, that is, 4 gauge measurements at 2 loads and at 2 temperatures to calculate a temperature compensation solution. The unknowns, or in other words, the TempComp solution, will be the resistor values for RS and some combination of RZ1 or RZ4 and RB2 or RB3. If this problem sounds like it's an optimization problem, it is. There's no way to solve the problem with a closed-form solution. The conditions constraining the optimization computation are, first, the bridge output at the reference load and temperature is some value. Second, the change in zero balance with change in temperature is zero. And third, the change in full-scale output with change in temperature is zero. In this video, we've gone over the theory behind the temperature compensation of a Wheatstone bridge that uses a resistor network. We've seen how adding a resistor, either in series or parallel, with a strain gauge will reduce its effective TCR. We've seen how adding a resistor in series with the bridge will reduce the bridge's rate of resistance change relative to the gauge factor's rate of change. We've also seen that the values of the temp-comp resistors need to be computed with a numerical optimization procedure. At Piezo-Metrics, we understand that not having a way to calculate the temp-comp resistances is an obstacle to using semiconductor strain gauges. To help everyone out, we're making our temp-comp calculator available on our website. To use it, the user simply needs to provide the gauge resistances measured at the zero and full-scale loads at the temperatures of interest, along with what excitation voltage was used and what full-scale bridge output is desired. If you're interested in accessing and knowing how to use this temp-comp calculator, a link is given below.